Hey guys, this video and lesson for calculus is from 2.6, and for pre-cal, when we start learning calculus at the end of the year, this is from section 4.1, and this section is called related rates. This is a very popular free response question that comes up in the AP test, and as we said in the last lesson, this is the application of implicit differentiation. So if you haven't watched the lesson on implicit, make sure you do so. This is where we start to see real world applications of implicit and how it works. We talked about the balloon inflating and how as time passes, the radius will start to change at one rate and then diameter will change at a different rate, and so will the circumference of the balloon, and so will the surface area and the volume. So before we start talking about how the questions work out, let's look at what basic shapes and derivatives with respect to time would look like. So last lesson we said with respect to x, so the denominator always said dx. Now because it's with respect to time, they're always going to say over dt. Okay? So obviously none of these variables here are t. We have x, y, and z. We have base and height. We have radius. We have height. Remember that pi is a number, so it serves as a coefficient. So that means that we will be doing our implicit step to every single variable here, okay? So one main shape you're going to be seeing is a triangle. If I were to do the derivative to x squared with respect to time, I'd do my regular derivative, 2x times implicit dx dt. Now the second term, derivative of y squared, is 2y implicit dy dt equals, and now the z squared would be 2z, and then implicit dz dt. Okay? If we were talking about area, this a doesn't just stay here by itself. We also have to do the rate of the area changing. So the rate of area changing would be dA with respect to time equals, and now we have half as a coefficient, and base and height are being multiplied, so we're going to have to follow the product rule. So we have first times the derivative of the second with respect to time plus derivative of the first with respect to time, and then times the second original. Okay? So the next common shape we're going to see is a circle. Two different formulas we can work with for a circle is circumference and area. So we start with the left, derivative of c for circumference with respect to time, dc dt equals 2 pi is a coefficient, so I'm going to bring down my coefficient. Derivative of r is just 1, but then with respect to time, implicit, we have dr dt. Okay? Area, derivative of a with respect to time is dA dt. And then remember, pi is a coefficient, so when I do power rule to r squared, that 2 is going to get multiplied to the front with the pi. So 2 pi r to the first power, and then it's implicit because it's with respect to time, so dr dt. Okay? And again, right now we're just practicing our implicit derivatives. We're going to start seeing this in application in just a moment, okay? Let's finish going over the shapes. The next three shapes we have are our three-dimensional shapes, okay? Our volumes. So we have a cone, a cylinder, and a sphere, okay? So for our first one, we have derivative of volume is dv dt equals, bring down your coefficient of 1/3 pi, and then r squared times h is product rule. So we have first times derivative of the second plus derivative of the first, 2r with implicit, times the second. Okay? Cylinder, derivative of volume, dV dt equals pi is a coefficient, so I'm going to bring down my pi. And then here, r squared times h is the same as this r squared times h here. So this is going to be product rule. And this inside is going to be identical to this inside because I'm multiplying the same two exact things. So first, times derivative of the second plus derivative of the first with implicit times the second. All right? And then our last one, sphere. This 4 over 3 pi is a coefficient, so be careful with that, okay? Derivative of volume with respect to time, dV dt equals, bring down your coefficient. And then here I'm going to do power rule. So I'm going to say 3r squared with implicit dr dt. Okay, and I'm going to take this one a step further because these 3's cancel out. And then I'm going to say, I'm just going to rewrite it. dV dt equals 4 pi r squared dr dt. Okay, so those are the major shapes you're going to be seeing, and just to get you rolling with their derivatives and practicing some implicit. Okay, so now the steps when you're going to do implicit, these are going to be in the form of a word problem, and we're going to do one of each shape in this video. Okay, take a moment and write these down. First, they're going to give you the word problem with a bunch of information, okay? You're going to start identifying the givens that they give you. The givens, once you determine what shape, could be volume, rate of volume, radius, rate of radius, height, or rate of height. So they can give you the bits of information from the function before the derivative, but the moment they say the rate of one of those variables, then they're talking about the dV dt, dH dt, or dr dt, okay? They could say increasing at a rate of, decreasing at a rate of, okay? So first you're going to identify all of those givens and which of the givens are missing, or which of these variables, I'm sorry, are missing, and that'll be the question that they're asking. You're going to make a sketch according to whichever shape, and you're going to label, okay? Now, once you figure out what shape you're working with, you're going to write down its equation. Then you're going to differentiate. You're going to do the derivative, which is what we just did here. Then you're going to start plugging in all the ones that were given, and hopefully you're just left with one variable that's left that you're going to be able to solve for, okay? So key words that you're going to find is the words changing, rate of change, or how fast. Those three words mean the derivative. So if I were to say, how fast is the radius changing, then they're asking for dr dt. If they say what was the radius, then they're just asking for r. We see the difference? Let's check out what these questions look like. All right, this first one says, a pebble is dropped into a pond causing circular ripples. Okay, so right here they're telling you the shape. The radius of the outer ripple is increasing at a rate of 1 foot per second. Okay, so see the word increasing at a rate with the word radius. Okay, then they say when the radius is 4, so when r is 4, at what rate, is the area of the water changing? Okay, so far we know we have a circle. Okay, let's see what's given. We know we have a circle, so if we're talking about radius and at what rate is the area. We had two equations for circles. We had circumference and area. But since they say at what rate is the area, that means I'm going to pick the area formula. Okay. The next given, we said the radius is increasing at a rate of 1. That means the rate, meaning the derivative of radius, so dr dt equals 1. Then it says when the radius is 4, so when r is 4, what, here's your question, is the rate of the area changing at? So if I said rate with the word area, it's not just area, it's the derivative of area. So there's step 1. I know what shape I'm working with, and I just spotted all of my givens. Okay? Step 2 is to do the derivative of the equation that you picked. So I picked area. The derivative of that is, derivative of A is dA dt equals, remember pi is a coefficient, so I'm going to do power rule. So 2 pi r to the first times implicit dr dt. Okay? And now your next step is just to plug in the information that you have. So dA dt is what I want to solve for. Okay? And then I have 2 pi. I was told to solve this problem when radius is at 4. And I was also told that the rate of the radius changing is 1. So dr dt is 1. Okay? So if I clean that up, I can say that dA dt equals 8 pi. And now the units of a rate of a first derivative always has two parts to it. You have the unit of measurement and then the unit of time. So if we notice, we can spot it here. It says that it was increasing at a rate of feet per second. Okay? So we're measuring this every second and by feet. So all you have to do is put feet per second and you are done with this question. All right, not too bad. Let's take a look at this next one. The top of a 17-foot ladder. Okay, so far we know this ladder is 17 feet. So the top of it is leaning against a wall and starts to slide down the wall. So if I have a wall, okay, and leaning on this wall, I have a ladder. Let's say this is my ladder right here. This ladder is 17 feet. Okay? So you can clearly see the shape that we're making is a triangle. Okay? And so far 17 feet is this part of the triangle, the hypotenuse. Okay, because obviously the wall and the floor make a 90-degree angle. Now it says it's leaning against the wall and starts to slide down the wall at a rate. So it starts to go down the wall at a rate. So whatever variable you give to this side, let's label it right now. So since we're used to graphs, this being x and this being y, okay, we'll say that dy dt, because it's the rate at which the ladder slides downward, of 2 feet per minute. All right. Now, something very important. I don't want you to just put the number 2 here, okay? Because there's a very important word here is that it's sliding down. So if this slides downward, then it's going in the negative direction. So dy dt is going down. Anytime you see the words down, left, decreasing, those are words to clue you in to put a negative, okay? Now the question says, how fast is the base of the ladder? So here's the base of the ladder, sliding away from the wall, Okay, so how fast lets you know they're talking about the rate. And then sliding away tells you they're talking about x. So what they're asking you here for is dx dt, right? And we can tell that answer is going to be positive because if I'm looking at this like a graph moving to the right, x's are positive. Okay, so sliding away from the wall. And then it says when the base is 15 feet from the wall. So when this base is at a location of 15 feet away, they're giving you that x is 15. Okay? Now, we had said if I'm working with a triangle, we can do area of a triangle or perimeter, which is Pythagorean. Here, we want to know values of the perimeter. Okay? So I'm going to work with Pythagorean. Now, here's a very important side note that you need to write. If a measurement is given to you that will never change, that measurement needs to put in before you do the derivative. For example, this ladder, assuming it's not one of those ladders that expand and condense, this is just a normal ladder, is 17 feet. No matter how much I move this ladder up, down, side to side, that ladder is always going to be 17 feet. That means I am allowed to plug that 17 feet in at the beginning of my question, okay? So my formula is specifically for this ladder scenario, x squared plus y squared equals 17 squared, okay? So again, if a value is given that will never change, then you can put that in before. And we'll see one more example where that happens later on. So step 2 is derivative. 2x to the first times the implicit. Now for the y squared, 2y times the implicit. And biggest mistake people make is they put 17 squared here. Remember, this is a constant. Derivative of constant is 0. So let's see everything that we can put in. Okay, I have 2 times x. They told me x was 15. Okay. dx dt is what I'm solving for, so that's okay to leave as a variable. Plus 2 times y. They did not give me y. Okay, but I do have enough tricks in my bag. I have enough information to be able to solve for y. So when this happens, I'm going to take a pause. I'm going to use this equation to solve for y. So I can say x squared, which if x is 15, let me rewrite it. X squared plus y squared equals 15 squared. So again, they gave me x squared, which is 15, so I could say 15 squared plus y squared equals 17 squared. Okay? Move this 15 squared over. Since there's no negatives, I don't really have to worry about my parentheses. And if you plug that into your calculator, you should get 8. Remember that every square root does have a positive and a negative, but because we're talking about the length, right, this measurement, we're talking about a positive number. So now that I have this 8, I can plug them right in. Okay. And now, so I'm moving on. I did 2 times y, which I found was 8. And then dy dt was given to me right here, -2. All right. And then equals 0. So I plugged in my givens. And one wasn't completely given. I had to use some clues there. And now all I'm going to do is solve for dx dt. So 15 times 2 is 30. dx dt. Okay. Minus 32 equals 0. All right, so hopefully you got 32 over 30. Do not worry about reducing. Don't stress it. It's not needed, okay? All we have left is to put our units. And if we look back at our question, we can see we were talking about feet and minutes. So we just put feet per minute, okay? And you are done with this question. All right, so this next question talks about a spherical balloon. So a sphere, it's just to let you know it's not one of these crazy irregular shaped balloons. It's a normal balloon in the shape of a circle. Sphere just because it's three-dimensional, okay? And now it's being inflated at a rate. So we hear the word rate, so we know we're talking about derivatives. Actually, we also know that it's a sphere. Let's go ahead and write that equation down. Okay, and then it says inflated at a rate of 8 inches cubed per minute. There are two bits of information here given to give you a hint as to what rate they're talking about. We know it's rate, so we know it's going to be a derivative. It's going to be d something dt. If I'm inflating a balloon, that consists of my air filling in the balloon, okay? So hopefully that gives you the hint to the fact that they're talking about the volume. If that doesn't click for you, the fact that it says 8 inches cubed, 3 in the exponent of the measurement always represents a three-dimensional measurement. So in this formula, I have radius and volume, which means because this is cubed, they must be talking about the volume. So again, the rate of the volume, they're giving you dV dt is 8, and it's being inflated, so it's positive. How fast, so they're asking you about a rate, is the radius. So they're asking you about dr dt. And it says increasing, which we know if the balloon increases, the radius grows as well. And then it says the instant that the diameter is 10 inches. Okay, so there's our given, there's our shape. Step 2 is to do the derivative implicitly of the equation we have. So we have dV dt equals, we multiply the 3 to the front, we bring down our coefficient. If you feel like you can do this faster, go ahead. I put that 3 a little higher so that it can look like a 3 over 1, by the way. And then implicitly is dr dt. Okay, remember that these 3's will cancel out. And now let's start plugging in what we know. Okay, dV dt they told us was 8. Okay, now I have a 4 pi. R, they technically didn't tell us, but they did tell us that the diameter is 10. And remember, diameter is double the radius. So if diameter is 10, now we know that radius is 5. And then dr dt is what they want us to solve for. Okay, so isolate that dr dt. I have 8 divided by, I'm going to divide all of this over 4 times 5 squared, which is 25, times pi. I don't like multiplying it all together yet, and I'll tell you why. Usually these reduce really nice. So I call this 4 times 25 because the 4 and the 8 can reduce, okay? And it's the mental math is a lot easier. So I'm just going to rewrite this in a different order. I'm going to say dr dt equals 2 over 25 pi. That pi is in the denominator. And then we were working with inches per minute. Now I know this one over here had a cube, but that's because they were talking about the volume's rate of change. We are talking about the radius's rate of change, which is a one-dimensional measurement, okay? So at this point, you are done with this question. Let's move on to the next one. This question says a conical paper cup, so we know our shape already, Okay. And then the volume of a cone. This is a three-dimensional object, so it will be volume. We have 1/3 pi. Feel free to call that pi over 3 if that seems easier to you. Pi r squared times h. Okay. It says that the diameter is 8, which means if diameter is 8, just like last question, I already know that radius is 4. Now the reason I need to write that is because my formula does not have a d for diameter, it has an r for radius. Okay? And the height is 6 inches. Now it says if water begins to leak out, so water starts to leak out at a rate of a 1/4 inch cubes per minute. So two things that should let you know what's going on. When water leaks out, the amount of water is the volume, okay? And also this number cubed should let you know that we were talking about the volume. So the rate of that water leaking out would be the derivative of the volume. Now it's leaking out. So that means that the amount of water as I leak out is decreasing. So that means it's going to be a negative 1/4. Okay? Leaking out. Very important there. Okay? Find, here's the part that's the question, the rate, so I know it's one of the derivatives, of the level that the water is dropping. Okay? So if the level of water is starting to drop at a certain rate, that is representing the height dropping. So what they're asking for is dH dt when the depth of the water is 2 inches. So specifically when the height is 2. Okay? Now don't let that confuse you with the height they gave you earlier. The height they gave you earlier is the full dimension of the cone. Okay? You're going to see in a moment why this comes in handy. So when the cone is filled with water, the radius is 4 and the height is 6. Okay? Now, as it starts to leak, they specifically want you to solve this problem when height is 2. Okay? So I'm going to bring back this paper where we had initially solved our cone. Okay? When I look at my cone, I have dV dt. This is one variable. R, dH dt, dr dt, and h. Those are 5 pieces to a puzzle. 5 missing variables. I need to make sure that if I'm going to solve it like this, I have at least 4 so that I can solve for the 5th. Okay? So, if I look back here, I can get dV dt with the equation, but here's my dV dt. I have an h. I can solve for an r. Remember, it's not this 4. 4 is when it's filled. I can solve for 4 when it's there. And then I'm asking for dH dt. That means that I have too many missing pieces of the puzzle because I don't know dH dt and I don't know dr dt. Okay? So, for that reason, actually, let me write it so you guys can see it. I'm going to put the words if. Okay? If I use the full derivative here, just doing the product rule. Okay. So dV dt I would be good here. R, I can create a ratio from these two so that I can solve for R here. Okay. Remember, I won't be using that one, so I would be okay with R. dH dt is what I'd be looking for. Again, I'd be okay with R. Now, dr dt I don't have, and I do have height, which is 2. So that means I have 2 missing pieces to the puzzle. I can't solve it with 2 missing pieces to the puzzle. I need to be able to isolate dH dt and be able to plug something in there. So what I want you to do is start figuring out the ratio between radius and height, okay? if we compare our radius as a ratio with the height, I can say I'm comparing 4 to 6. Okay? So that means if I compare radius divided by height, I can say 4 divided by 6. Now, I want to get rid of one variable. Okay? Since I need to solve for dh dt, I'd rather keep my heights and get rid of my radiuses. Okay? So that means I would have to isolate our radius to be able to plug it in and change it in terms of h. Let me show you what I mean by that. If I want to isolate r here, I would multiply my h over, and I can say that radius is equivalent to 4/6 of the height, or we can call that 2/3 of the height. So let's rewrite our volume formula using this rule. So I can say volume is 1/3 pi. Instead of saying r squared, I'm going to rewrite r in terms of h. 2/3 height squared, so this was my r, times height. If I clean this, remember that squared belongs to both, so I'm writing 4/9 h squared for this one times h. I haven't done a single derivative here. This is all happening before the derivative to clean so that I can use what was given to finish solving this problem. If I finish cleaning this, I can say volume equals 4 pi over 3 times 9 is 27 h to the third. And now, according to this specific cone, whose ratio was a 4 to 6 radius and height, I rewrote my volume equation in terms of just height. So now I'm going to have more than enough information. So now go ahead and do the derivative. Okay, here's what I'm doing. Deriv. So dv dt equals, I'm going to multiply the 3. I'm going to literally write it as 3 times 4 instead of multiplying that as a 12. I'll explain why in a second. And then h to the second power, and then implicit dh dt. So now what I need to plug in is dv dt, which I have, h, which I have, and dh dt is what I'm solving for. Now this is a much easier question, okay? So the reason why I didn't multiply that 3 and that 4 is because almost always it's going to be so much easier to reduce before you multiply. So if I would have called this 12 over 27, you might have had a hard time reducing. But a 3 and a 27 are very easy to reduce, okay? So now I can keep going and plug in the givens. dv dt is a negative 1 over 4. And then I have 4 pi over 9 times h squared. They said h was 2, so 2 squared. And then dh dt is what I am solving for. Okay, I'm going to come up here so I have a little more room. So now just start working on isolating this dh dt. So I'm going to say negative 1 over 4 equals 2 squared is 4. 4 won't reduce with 9, so I can go ahead and multiply that 4 with this 4. And I can say 16 pi over 9 dh dt. Now I'm going to take this slow, but if you feel confident in going faster with this, feel free to. These were being multiplied, so I'm dividing it over, and when I divide fractions, I multiply by the reciprocal, which just means that I'm going to keep, change, flip. And now I'm just going to write this in the right order. dh dt is equal to negative 9 over 64 pi. And this is a rate, and this is height, so it's one-dimensional. And we had said we were working with inches and minutes. So being that it is inches per minute for a one-dimensional object, I don't need an exponent on that inches. All right. And there is my answer. All right. This one was a trickier one, okay? I'm letting them get a little more difficult as we go. We have one left. All right, last example, a cylindrical oil tank. Okay, so we know it is a cylinder. Okay. Bear with my drawings there. And it says that its radius is 12 feet. So let's write the formula for a cylinder. Okay, and then they gave us radius is 12. Good, so I have the R. The height is 8. Now I have the H. Okay, and it is being filled at a rate, so filled at a rate of 16 feet cubed per minute. So if I fill this with something, it's going to take up the inside, which means it'll fill up the volume. But again, if you don't catch that wording, remember this cubed should let you know. So letting you know that dV dt is going to be 16. At what rate, so here's the question, and it's going to be a derivative, is the height of the oil, so what is dH dt, when, the instant that the tank is half full. So if it is half full, we're talking specifically about when the height, okay, half full, if the full height of this is 8, then we're talking about when it is 4, okay? So now something very important to remember about cylinders, okay? And you can write this as a side note. It would happen every single time you're working with a cylinder. And it's back to the same concept as the triangle, okay? In the cylinder, whether I'm completely full, partially full, halfway full, barely full, the radius of a cylinder never changes, okay? So just like that ladder was 17 feet and it would never change, we plugged that 17 in before we did the derivative. Since the radius will never change here, I get to plug this in before. So I'm going to rewrite my volume. And now I can continue on and do my derivative. So derivative of volume is dV dt. This is a coefficient. Derivative of H is 1, and then implicit is dH dt. Okay? So as long as you remember that information that doesn't change, like in a cylinder is radius, that goes in first, this problem is actually very, very simple. Okay? So let's plug in what we know. dV dt is 16. And then dH dt is what I'm solving for. Isolate it. So I'm going to divide this over 16 over 144 pi equals dH dt. Okay? Again, you don't have to reduce. If you did, you would be writing dH dt equals 1 over 9 pi. Again, not needed though. And then height is a one-dimensional object, but since it's a rate, I do need to put that feet per minute. Okay, and you are done with this problem. So let me address something really quick with you. You might be asking yourself, well, why in the world did they give me all this information about the height was 8 and now it's down to 4? In the cone, right, when we were working with the cone, because of its triangular shape at the bottom, as water starts to leak, I have less and less water for it to leak, right? The radius changes, the height changes. In a cylinder, whether I'm filling in or taking out, because this measurement never changes, it is the same amount that is leaving every single time, whether I'm up here, in the middle, or down here. That's why my rate of the height changing will always be the same amount, no matter what height it is. That's why it wasn't necessary to plug in a height, right?